In this video, we're going to look at the basics of calculating different forms of energy and combining them together into the conservation of energy. All right, so there are a couple of calculations here that you might be familiar with if you've worked with energy in another class before. You may recognize this one. This is our kinetic energy. IB is going to refer to it as E with a subscript of K. So 1/2 mv squared. I will use KE to talk about it. It's the same idea. And then delta EP, the IB notation, I will call it GPE to represent the gravitational potential energy. Now, these are in this video the main two types of energy that we're going to be focusing on and calculating to compare. These are often referred to as mechanical energy. We will see lots of different forms of energy later on throughout this class. So let's start by comparing here. We've got Usain Bolt at 100 kilograms running 7.67, and this man at 100 kilograms on a diving board 3 meters up in the air. Well, Usain Bolt is moving, so there's kinetic energy. 1/2 times the mass times the velocity squared. I'm getting 29 or 2,941 joules. Joules is my unit for energy. That is true for all forms of energy that we will see throughout this course. Gravitational potential energy is mass times gravity times height, 100 times 9.8 times 3. You'll notice here when we are doing energy, we are not worrying about a direction, so we're going to use a positive 9.8, even though sometimes you may have used a negative 9.8 when we talk about acceleration of gravity. So here, if I'm calculating a gravitational potential, I plug those in, I get 2940, so 2,940 joules. You'll notice that they are about exactly the same. Usain Bolt technically has more, but it's kind of rounding based on the form of gravity that we are using here. So the important thing is we can compare very different types of energy, and those types of energy will convert one to another as we are going through. So it is important that we can understand some relationships. If these are our main types of energy that we are looking at today, how does the gravitational potential energy change when you triple the height? Well, if you look at our equation, elastic or gravitational potential energy is on one side and mgh is on the other side. Height is all by itself. It's not squared, it's not cubed. Nothing interesting is happening in that fashion. So we say that it's a direct relationship between gravitational potential and the height. So triple the height will give you 3 times the gravitational potential energy. If we look at kinetic energy and how it changes when you triple the velocity, you'll notice kinetic energy is on one side and then v squared is on the other side. That's not perfectly a direct relationship. So if I triple the velocity, I'm actually gonna get 9 times the kinetic energy because 3 squared is 9. If I double the velocity, 2 squared is 4 times the kinetic. If I quadruple the velocity, 4 squared is 16 times the kinetic energy. Now, we can conserve this mechanical energy. Basically, that is just saying for a closed system, the total energy before is equal to the total energy after. That this diver here, standing up at the top, has a potential energy of 15,000 joules and a kinetic energy of 0 joules. All the way at the bottom, I expect the same total energy of 15,000 joules, but now the potential is 0, so the kinetic has to be 15,000. In the middle, we have 7,500 joules of potential. The total still has to be 15,000, so the kinetic has to be the other half. And then at these other points, we will see that it will also add up. So we can find the kinetic energy basically taking 15,000, subtracting out the potential. Now, one of the things you should notice is as something falls, the potential energy decreases because the height is going down, and then the kinetic energy is increasing by the same amount that the potential changed. So we will see as the height decreases, the velocity increases. And that is something that we know from before, but the total is always going to be the same. Now we can do this mathematically as a full equation. Here's an example of something that we've been able to solve using kinematics and SUVAT. But let's do it here with energy. A 2 kilogram ball is released from a height of 20 meters. What is its velocity when its height is decreased to 5 meters? Well, we're going to say that the initial energy is equal to the final energy. Right now, we only know two types of energy. So I'm going to say the total energy before, gravitational plus potential, our gravitational potential plus kinetic, is equal to the total energy after, GPE plus KE. And then I look at what I've got. Up here, I've got some gravitational potential energy, but there's no kinetic energy because there's zero velocity. And then down here, there's still some height. So I'm going to say there's still gravitational potential. But now it's also going to be moving. So there's kinetic energy there. This is my initial. This is my final. So I can just cancel out that kinetic energy. I wouldn't have to. I could put 1/2 mv squared where v is 0. It would just become 0. I wouldn't have to worry about it. But now I'm going to use this shorter form and then plug in the equations. mgh initial is equal to mgh final plus 1/2 mv squared. And then I plug in my numbers. I got a mass of 2, gravity is 9.8, the initial height is 20, mass is 2, 9.8, the final height is 5, and then my mass is 2. The only thing I don't know is v. I do some algebra here and solve for v to be about 17.15 meters per second. Okay, so my initial equals my final, and then I can solve for my final velocity. Here's another example problem. The height of a building that Spider-Man in the first Spider-Man movie starts off as 6 stories or 18 meters high. The height of the building he wants to swing to is only 3 meters high. Tobey Maguire, the actor for Spider-Man, has a mass of approximately 72 kilograms. Let's use conservation of energy to calculate the speed when the feet touch the roof. Now, in this particular example, we can't actually use kinematics and free fall because as that swing is happening, there's a direction change. So there's some more complex things that are going on. But it is true that the initial energy will still equal the final energy. So if I have gravitational potential plus kinetic initially, and then GPE plus KE final, knowing that we're starting from rest, I can basically solve this as we did before. Plug in my equations, ignoring my initial kinetic energy being 0, taking that out and then plugging in my values. My mass is 72, my initial height is 18, my final height is 3, and then my final velocity is unknown. I can plug this in steps and then find that the final velocity is 17.15 meters per second. Now, it's weird. That was the exact same answer that we saw in the previous example of the ball that was falling. Turns out I knew that. They were going to be the same from the beginning. Now, there are some things that are similar about these. There are some things like gravity is the same. They're on the same planet. That is happening. You can also see that there was no initial kinetic energy. So our format of this equation was the same for both of them. But the biggest similarity is the final velocity is the same because they have the same height change. So the same height change, one went from 20 to 5, one went from 18 to 3. That's a change of 15 meters. And turns out the mass doesn't matter. So if the height changes the same, and you have the same setup of all gravitational potential becoming GPE plus KE, you're going to get the same final velocity regardless of the mass. So if mass doesn't matter, what if we're not given a mass? So here we have the biggest marble run of all time. This marble of unknown mass starts out at 100 meters, goes around a loop to loop with a height of 70 meters, and then carries on. My initial energy, we're going to say, is all gravitational potential. And then my final energy, again, is GPE plus KE. It's not always going to be this, but we'll see it one final time here. So we're starting again from rest, which means we can, once again, cancel out KE, and then plug in our equations. Now, one of the things that we've been doing throughout is we've been plugging in every single value, but here we don't have a value for mass. Turns out we could have done this on the other problems as well, but since mass shows up every single time, we can just cancel it out. Every single term includes a mass, so we can divide mass out by everything, and it doesn't matter what the mass is. So now I can plug in what's left. I'm not calculating true energies anymore, but I can still compare to solve for an unknown, and I can find that a final velocity of this marble here at the highest part of this ramp, or this loop-to-loop, is about 24.2 meters per second. All right, this is true of projectiles as well. So if we see a projectile here that starts off at 20 meters per second, angle of 755, and it goes like this, we can solve our triangle and figure out what my x velocity and my y velocity are. Well, my x velocity is something that I know. I know it's 11.5 if I do this triangle, and the x velocity is the same for the entire projectile. That's something that we learn in our understanding of projectiles. There's nothing accelerating, speeding you up or slowing you down in the horizontal direction. So now I know an initial velocity and I know a final velocity because there is no vertical component of that. So I know it starts at 20 and it ends at the highest point at 11.5. I can use that to figure out its height using energy. I could do that with projectiles as well in kinematics, but let's see how we can find this height using an energy equation. The initial energy is equal to the final. Now I have no initial potential energy because I am starting at the lowest point. All of my initial is kinetic. At the highest point, I once again have gravitational and kinetic energy. So my equation turns out to be 1 half mv squared is equal to my final mgh plus 1 half mv squared. The mass cancels out. I don't care about the mass. And I can plug in my initial velocity of 20, my final velocity of 11.5, and the only thing I don't know is the height. And calculate that the height, it goes up 13.7 meters. If you solved for the initial vertical velocity and then also did your kinematic equations to figure out the height when the final velocity is 0, vertically, you would get the exact same answer. So it's just yet another tool in your toolbox to be able to solve for an unknown in a before and after sort of scenario. All right, let's look at one more scenario where the mass is never going to be possible. Here we have water at the bottom of a waterfall that has a velocity of 20 meters per second after it falls 16 meters. What is a water speed at the top? So it helps for me to think of like what is the initial and final energies that are happening. Well, initially, or a final, let's start there. I know that we have a velocity of 20 meters per second, so there's some kinetic. And then up at the top, we know it has some gravitational potential because there's a height that's different than it was before, and then some kinetic energy because the water is moving as it goes over that waterfall. We're going to say that final has no gravitational potential. We are going to declare that to be our ground zero. So there is no height there. All of the height is up at the top. So we have no final kinetic or gravitational potential. We plug in what we know for our equations, and then the mass cancels, and we're left with just the initial velocity being unknown because we know that the height is 16 meters and the final velocity is 20 meters per second, which allows us to find that the initial velocity is less than 20 meters per second, is 19.3 meters per second as it sends off the top of that waterfall. All right, so takeaways here. You should be able to describe and calculate the simple kinetic energy and gravitational potential energy. Explain the implications of conservation of energy and show that the total mechanical energy ends up being the same. It's just a different breakdown of kinetic and gravitational potential for these examples. Be able to interpret a scenario and set up an equality based on the energies present at different locations, and then use conservation of energy to solve for an unknown energy in a variable or variable problem.